Now this is the implementation part of our oxidized silicate hull ore leaching example introduced in my previous video. Now let's start off by looking at our custom built example library. The first key unit block is this metallurgy domain reference block, which each flowsheet model needs to be connected to. This block defines our flowsheet model variable parameter space. For the sake of this video, we only have a single atmospheric leaching tank that overflows to an infinite volume reservoir called an infinite sump block. We then also have an atmospheric feed block for the gas, because air may need to flow into the tank, for example, if there's a sudden drop in a tank level. This is just one simple example of the physical reality included in our models. And then we have our ideal feed blocks. Now, to keep this video short, I've made a few copies of this block and gave each feed stream a unique name after specifying typical stream compositions. So we have two slurry feed stream blocks for imposing interesting mineralogical dynamics on the leaching vessel. Now then we also have a concentrated acid makeup stream and a raffinate recycle stream. Now these stream specs would usually be entered by the user or be solved over time in an integrated circuit simulation. So these are the only custom built Simscape physical domain blocks utilized in this example. These Simulink helper blocks on the right hand side have been added to the library, again only for the sake of keeping this video short. These subsystems constitute standard Simulink library blocks that you, the user, would be free to build and or expand for your own purposes. Alternatively, we will build these if the user is not yet familiar with the MathWorks products or when kicking off a new project. As mentioned in my previous videos, we would match the experience and situation of each end user. Let's drag all these example blocks to our blank template. So first step, we connect the reference block to the solver configuration block. And let's make the leaching tank a bit bigger. And then we can connect our ideal air or gas source block to the reference, and then to the first input node of our leaching tank block. And then we could add our two ideal slurry feed blocks. Now on a real plant, this would be a single pipe coming from the comminution circuit, but here we want to play around a bit with the particulate feed containing different minerals in different size classes. This allows evaluation of the impact of mineral variation, at least up to a point where the mining and comminution circuits are also added. Now let's add the acid makeup and raffinate ideal feed blocks. Obviously, if we had a downstream solvent extraction circuit, there would be no need for an ideal raffinate feed source. This would be simply a recycle stream connected to the last input node of our tank. Now by double clicking on the tank block, you can see the description to make sure that we connect the correct feeds with the correct input nodes, as well as all the other information required. So now we look at the output side. Firstly, we can connect our vent stream to an infinite sump block. Now we make use here of a standard Simulink source block constant. Now I've actually pre-named these constants for the sake of saving video time, so I'm simply going to drag these constants off the list. So by making this first constant 1, we essentially keep the sump of the vent at the default atmospheric pressure. Similarly, the slurry overflow pipe is connected to the next sump. When adding a series of leach tanks, this line would obviously be connected to the second tank in the cascade arrangement. The tank underflow pipe is also connected to the next sump, but unlike the other sumps, some large pressure specified. Here we specify 1e to the 7 pascals or 100 bars to make sure we prevent the tank from draining through this pipe. Finally, the sampling and spillage line is also connected to a sump block. Here we could impose any upset on the circuit we like, for example to simulate major spillages on the circuit performance. For now, let's keep this flow 0. Now there's no external heat transfer in this example, so let's make this heat flow 0 joule per second. So we basically have an adiabatic tank other than for the energy flows via the process pipes. Next, let's quickly set the inflow fractions. Let's make each of the two slurry feeds 50%. In other words, the total flow rate is correct and split equally between these feeds. The raffinate recycle stream is what it is, so we set this fraction equal to 1. Now we can add our cumulative mineral and metal extractions calculator, which I've already set up. Now because we have those two slurry feeds, we have to use a standard Simulink math operator addition block to add their signals together. So let's find that signal addition block, which is right at the top. So it's simply a matter of connecting the correct measured outputs to the correct calculator inputs. So in this calculator we basically divide the integrated mass reacted by the integrated particle inflows and the original inventory masses that was in the tank when we started. Now let's also make use of standard Simulink display block. Here we connect our display block to see how the solution tenors vary over time in the simulation. Finally, let's add a pH controller to the leach reactor. Now I'm not sure this would be the way that the first leaching reactor would actually be operated on a real plant, but let's add this for illustrative purposes. So the tank molality vector output is connected to the sensor input, which is connected to the proportional integral controller, which in turn controls the concentrated acid fraction added. So by the way, we have already developed solution thermodynamic blocks that can be used to speciate the solution and calculate other thermodynamic properties dynamically. I shall illustrate examples of this in future videos. So all that remains now is to set the other output ports and displays where required, and I will do this quickly, neaten up everything and also add a few scopes. Okay, so here is the cleaned up flow sheet. For the sake of conducting lots of different simulations in quick succession, we add most parameters in a MATLAB script file. Here, for example, you can see the comparative particle size distributions of the two feed pulp streams. The blue graph represents the finer composite particles containing most of the zinc minerals, while the red graph represents the coarser particles containing most of the gangue minerals. As you can see, I've temporarily set the inflow fractions to 0 and also made the overflow sump pressure high, so that no particles flow into or out of the leaching block. So we basically have a batch leaching vessel, and the reason for doing this is to show that the number balance is preserved, which is an important quality control check. Firstly, let's look at the extractions over time. Here you can see how fast the minerals react in the system if enough acid is added. Looking at the number balance, we are talking about 40,000 particles miscalculated in the tank containing 4e to the 17 particles. This is an insignificant error of 1 preceded by 13 zeros, and this is for a fast leaching worst case scenario in terms of the numerics. Now that we are happy with the numerical accuracy, the pH controller is set to a value of 1, and I've also reset our original feed fractions and slurry overflow sump pressure. So now we are basically running a dynamic continuous reactor simulation over a 56-hour period. Let's just zoom into the extraction values as we run a simulation, and you will see that the mineral behavior is now very different compared to the batch reactor, as one would expect. Now, as shown before, the results explorer can be used to access all the variables at any point in a circuit. However, when working in a team where not everyone may all the time have access to our SimScape models, we may want to set up a standardized Excel template where the important outputs are written to. So the user can quickly look at all the results at once and email it to the other team members. Here I've set up plots of the reactor solution tenors, the residue composition, the composite phase mass breakdown, and a fraction of the precipitated silicates that is crystalline as opposed to amorphous, which would be important when connecting this model to a downstream liquid-solid separation blocks. Here are also plots of the cumulative mineral phases and elements reacted, and you can see that the pH was nicely controlled at a value of 1. The tank was half full when we started, so this is the level of the slurry overflow pipe, and the average residence time was eventually just over 1 hour. And then we can look at the pulp densities flowing into and out of the tank. Now the acid consumption stabilized out at around about 75 kilogram acid per ton of ore in this tank. Also, you can see that the reaction heat kept the tank at about 48 degrees Celsius. Now this temperature would go up if we add concentrated acid faster because of the dilution heat effect and also the increased leaching rates. Finally, we look at the total elemental mass flow variation around the circuit to see when we actually reached steady state, and also the fact that this curve collapses to 0 is used as a check that no stoichiometric errors were made. Now we run a 3D plot function, and you'll see that the unaltered composite particle mass virtually disappeared when there was excess acid at the start. But then we reached a new state as determined by the intrinsic ore reactivity. Also, the distribution became coarser over time, which is counterintuitive. The reason for this is that the finer particles contain more surface area, so per unit volume material, more mass is transferred to the liquid phase, causing the total distribution to shift the other way. Finally, let's quickly look at an upset in a composition of our feed ore. The induced upset can be any function of time. Here I've made it very simple, so let's run a simulation to see what it looks like. Now the total feed rate stays constant, which is not really required, but done here so that we vary one input parameter and then measure the system response. The two slurry scopes are linked together so that you can see that each line feeds at 50% or 25 kilograms per second. And now you will see the drop in the zinc containing minerals content with a corresponding increase in the gangue minerals content. Here you can see the zinc tenor dropping temporarily because of this mineral flow upset. Also, because the zinc minerals are more reactive and finer than most of the gangue minerals, we see this drop in the temperature as the leaching rate dropped, which then recovered again. We have now run out of time. Thank you for watching this video, and please visit our website.